general relativity step by step. I'm going to consider, we've considered the 4 momentum, P I think that was, the 4 velocity, U we usually use, and of course the 4 displacement, S I think I used for that, all of which are 4-dimensional, well, 4 vectors. I'm going to introduce a new one called N, which is equal to the number flux density. Number flux density. We're going to get some practice with modifying this particular 4 vector. I'm going to set up some coordinates here. There's an X and there's a T, and I'm going to consider little particles moving around, little atoms. Sometimes I call them atoms, sometimes particles, sometimes dust particles. And I'm going to consider a little control volume here, and the volume I'm going to consider continuum mechanics. It's going to have to be large enough so the number of particles is large. It's going to have to be large because I want to apply continuum mechanics to it. I want to apply differential infinitesimal calculus to it. But it's also got to be small, because if I draw a little box and I've got some particles moving leftwards, I don't want the box to be big enough to contain particles moving in different directions. So it's got to be small, because all particles must be moving in the same direction. Now what I wanted to do is to define, so that's perfectly standard stuff. I mean, we know how, I mean, my original training is in fluid mechanics, and I'm very used to taking control volumes that are big enough so you don't need to worry about individual molecules, but small enough so that all the fluid inside your particle has got the same velocity. And it's the same here, it's no big deal. Now I'm going to define N, which equals the number density. Number density. Well, it's a little bit less straightforward. Equals number of particles per unit volume. And I'm going to put that in scare quotes because I'm not being sufficiently precise here. If I set up a coordinate system here, there's me, and I've got an X and a T coordinate, and I define a little sort of volume here, V. Well, that looks perfectly well defined until I ask my friend Baz, who's in his spaceship. Here he is. There's his spaceship. There he is, Baz, and he's cruising along here. What volume does Baz see? Well, Baz measures my control volume here. Instead of X, Y, and is that? No, that's Y, and that's Z. Well, Y is the same for everyone. Z is the same as everyone for everyone. But X goes to X root 1 minus beta squared, where beta equals his velocity normalized to the speed of light. And this thing here is called the Lorentz contraction. Effectively, you'll remember the Lorentz transforms gamma, beta gamma, and gamma. Effectively, it's that term there. So, Baz, so me, I say the volume is X times Y times Z. Baz says, no, it's X times Y times Z times root 1 minus beta squared. So we disagree about the volume of this box because Baz has got a Lorentz contraction to deal with. Well, I have got his Lorentz contraction to deal with. So this quantity here, number density per unit volume, is problematic. It makes sense to consider. You see, normally you haven't got a preferred reference frame, but with particles in the picture, especially particles where we're considering a control volume that's big enough to have lots of them but small enough to have the same velocity, particles do have a preferred reference frame. The one where they are at rest, where the particles are at rest. So if I've got my coordinate system here and there's a whole bunch of particles moving over there like that, well, I'm going to consider a coordinate system which looks like that, x bar and t bar, as opposed to my original one, x and t. And in the barred coordinate system here, x bar, t bar, the particles are at rest. And that is a perfectly well-defined concept. And here, n equals the number density in this particular frame. It's a bit like rest mass. It's the mass of the object in the frame in which it is at rest. And I'm going to define n, which equals the 4, there's different people call it different things, but I'm just going to call it the 4 number flux. The number flux. 4 number flux vector. 4 vector, oh well anyway. N equals nu, where u equals the 4 velocity of the particles. So we can write it out. So because we know what u is, and I'm going to write it in a column vector, it's gamma, gamma u, gamma v, gamma w, where u, v, w is the 3 velocity. U, v, w is the 3 velocity. We know that n equals nu equals gamma n, gamma u, gamma v. Sorry, that should be gamma n u, gamma n v, and gamma n w. Where of course gamma equals 1 over root, my writing, 1 over root 1 minus beta squared. And that is the definition of the 4 number flux. It has got the same relationship to flux as velocity has to 4 velocity and momentum has to 4 momentum. It's a nicer, cleaner, clearer, simpler way of thinking. And I'll show in the next screencast that it's got an absolutely astonishing property. Well, I think it is anyway. I guess other people aren't quite as impressed with it as I am. But anyway, I'm going to stop there. Stop. There's the number vector.